What? Winkler foundations or elastic springs?
I'll briefly present how to analyze a beam on an elastic foundation using the finite difference method based on the approach proposed by Malter. The basic concept is that this analysis is based on the Winkler foundation model, where the soil beneath the beam is idealized as a series of discrete springs. Each spring provides a reaction force proportional to the local deflection of the beam. Malter proposed using the finite difference method to numerically solve the differential equation of the beam. The beam is divided into multiple equal segments, and the deflection at each point, yi, becomes a variable in a system of equations. So, when using finite difference approximations, the average slope is and the central difference for second derivative is this is a very important equation, and these expressions approximate the curvature of the beam.
So when modeling the soil reaction, as shown in two figures, the spring reaction force at each station is given by general station is and end station is so given fractional rigidity EI and subgrade modulus Ks, the equilibrium at each node becomes this balance the beam's bending resistance with the foundation reaction and any applied loads. So applying these to our stations, we form about an equation, boundary condition, and force equilibrium must also be satisfied. For example, this ensures particular force equilibrium. The finite difference method offers an efficient numerical approach to solving beam on elastic foundation problems. It is especially useful for computer-based structural analysis and has practical applications in foundation design.
Hello, Professor. Thanks for giving this precious chance to present our Winkler Foundation research. In this presentation, I'll introduce the MATLAB program we developed for analyzing a Winkler foundation. This program calculates deflection, shear force, and bending moments in a continuous footing subjected to multiple laws. It's designed so that the user can directly specify the number of laws, their magnitudes and locations, as well as the number of springs used for discretization. The first part of the program handles user input. So you can see this is input part. It begins by taking the modulus of elasticity, foundation thickness, foundation width, foundation length, and the subgrade reaction coefficient, which represent the stiffness of the supporting soil. Then it asks for the number of springs used to discretize the footing, as well as the number of point loads, and finally the magnitudes and location of each load, which are input as metrics. After collecting the input, the program moves on to compute the basic structure parameters and construct the coefficient matrix A. So to divide the footing into equal segments, it calculates the spacing h equal L divide n minus 1. Then it builds the coefficient matrix A. So you can see here for the A part, which reflects both the flexural rigidity of the footing and the subgrade stiffness from the Winkler model. This matrix formulation leads to the linear system A multiple y equals B, where y is the deflection vector and B is the load vector. An important point here is that since the size of matrix A depends on the number of springs n, and each element follows a specific pattern, loops are essential to efficiently generate the matrix. In other words, for loops are used to automatically assign values to each element of the matrix based on its position and role. So you can see this A part use for loop very essentially. The upper and lower triangular positions of A, as well as specific entries based on boundary conditions, are all constructed using nested for loops. Next comes the construction of the right-hand side vector B. And now I'll show you this part of vector B, which represents how the external loads are distributed and accumulated across a footing. Depending on where each load is located, the corresponding values in B are adjusted accordingly.
Once the system A multiply y equal B is constructed, we solve for the deflection vector y. Although this can be done using inverse A multiply B like this in this MATLAB, this solution gives us the deflection at each node. Using the deflection values, we then compute the moment at each location by applying the finite difference approximation of the second deliberate. Boundary moments at the two ends are set to 0 here. Shear forces are computed by accumulating spring reactions across the footing. As loads are passed, the shear force graph drops discontinuously to reflect the concentrated force, creating a piecewise linear shear diagram as expected in structure behavior. Once the calculations are complete, the program displays the numerical result in the command window down here. Deflection, shear force, and moment, and simultaneously plot 3 graphs. Deflection curve, shear force distribution, and moment diagram. These graphs are drawn using subplot so that all can be viewed within a single figure window. The main features of these programs are as follows. First, the user can freely configure the number, location, and magnitude of point loads, making the tool flexible for analyzing various design cases. Second, by using the Winkler soil model, the program realistically captures the interaction between the foundation and the supporting soil. Third, by adopting a matrix-based numerical analysis method, the program ensures both computational speed and accuracy while also being easily extensible. Lastly, the use of for loops to construct matrices is a crucial part of the code. It plays a key role in ensuring both computational efficiency and mathematical consistency when implementing the system equations. Thank you for listening to our presentation.
This is our graph about deflection, shear force, moment.